All right, just going through some troubleshooting real quick. That's on. That's on. Why is it not showing up? Oh, I don't know why it does this. That's why I don't use these. Never mind. For some reason, it connects weird and it just doesn't work right. I hate it when that happens. Okay. Uh-oh. The heck? Sorry, I'm just having some issues right now. There we go. Let's just do that. Okay, there we go. Got the music going. I'm going to go ahead and finish up chapter 1 of that organic chemistry textbook. That is the plan for this session. So I'm going to go ahead and scooch you forward just a little bit. All right, so we were on 1.6. So this is OpenStax organic chemistry, whatever edition it is. Yeah, it's not on the save file, so whatever. We're on 1.6, sp3 hybrid orbitals and the structure of methane. So first, let's do a little clarification. So basically, if I have, boop, 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 boop. Let's just say these are hydrogens. This is methane. Using the Lewis structure, it should look like a flat substance with all 4 hydrogens within some sort of square plane. But that's not what is seen in experiments. What's seen in experiments is, so each of these lines is in the plane. So you can imagine between these hydrogens, there's a triangle. Hydrogen, carbon, hydrogen. Makes it kind of like a triangle. And then you got one hydrogen sticking out of the plane and one hydrogen pointed in towards the plane. And so you get, I always do it like this. I make, I point my, like if I were to stick my index finger, my thumb, and my middle finger all together and then spread them out equal distance from each other, I should be able to make like a triangle out of that. And then I have my arm pointed in towards me, and so I can play around with my hand and just demonstrate. Oh, these two are on the plane. One sticking out, one sticking away, and so it's a cool little thing that I learned how to do. So, but sp3 hybridized just means that all of the electron domains, the directions the electrons are pointed, are going to point in equal and opposite directions from each other, in 4 equal and opposite directions from each other, and that's why it's a tetrahedron. But that's more general chemistry. I won't get into much detail for that. All right. The bonding in the hydrogen molecule is fairly straightforward, but the situation is more complicated in organic molecules with tetravalent carbon atoms. Take methane, CH4 for instance. As we've seen, carbon has 4 valence electrons, 2s2, 2p2, and forms 4 bonds. Because carbon uses 2 kinds of orbitals for bonding, 2s and 2p, we might expect methane to have 2 kinds of CH bonds. In fact, though, all 4 CH bonds in methane are identical and are spatially oriented toward the corners of a regular tetrahedron, as shown previously in Figure 1.7. How can we explain this? An answer was provided in 1931 by Linus Pauling, who showed mathematically how an s orbital and 3p orbitals on an atom can combine or hybridize to form 4 equivalent atomic orbitals with tetrahedral orientation. Shown in Figure 111, these tetrahedrally oriented orbitals are called sp3 hybrid orbitals. Note that the superscript 3 in the name sp3 tells how many of each type of atomic orbital combine to form the hybrid, not how many electrons occupy it. So yeah, sp3 just means you're using all 3 of your p orbitals. So you're taking your s, and so if you just do that one, plus, oops, that's an L, plus the 2py plus 2pz plus 2px, you get 4 times sp3 orbitals. And then what they do is they orient themselves relative to each other. And so in order to get the best possible angles between each thing, you just do equal and opposite. So, well, all 4 of them thinking that way. So they're all equal distant from each other. So this angle from that hydrogen to that one is the same as this one to this one, same as that one to that one, same as these 3. All of those are the same angle. Okay. The concept of hybridization explains how carbon forms 4 equivalent tetrahedral bonds, but not why it does so. The shape of the hybrid orbital suggests the answer to why. When an s orbital hybridizes with 3p orbitals, the resultant sp3 hybrid orbitals are unsymmetrically about the nucleus. One of the 2 lobes is larger than the other, and can therefore overlap more effectively with an orbital from another atom to form a bond. As a result, sp3 hybrid orbitals form stronger bonds than do unhybridized s or p orbitals. The asymmetry of sp3 orbitals arises because, as noted previously, the 2 lobes of a p orbital have different algebraic signs, plus and minus, in the wave function. Thus, when a p orbital hybridizes with an s orbital, the positive p lobe adds to the s orbital, but the negative p lobe subtracts from the s orbital. The resultant hybrid orbital is therefore unsymmetrical about the nucleus and is strongly oriented in one direction. When each of the 4 identical sp3 hybrid orbitals of a carbon atom overlaps with the 1s orbital of a hydrogen atom, 4 identical CH bonds are formed and methane results. Each CH bond in methane has a strength of 439 kilojoules per mole and a length of 109 picometers. Because the 4 bonds have a specific geometry, we also can define a property called the bond angle. The angle formed by each HCH is 109.5 degrees, the so-called tetrahedral angle. Methane thus has the structures shown below, or shown in figure 112. Yep. So if you were to have like little balls connected by little lines, you could rotate this molecule around. And there's actually some good videos that you can do, and even some GIFs, I guess. I forget if it was. Yeah, I think it was GIF. Is there the controversy for that? Water break. 1.7. sp3 hybrid orbitals in the structure of ethane. This is where you start to get rotations and different conformations. So there's a difference between conformation and configuration. A conformation, you don't have to break a bond. A configuration, you do. So if I were to do like boop, boop, boop versus boop, 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 that's a configuration, because that pi bond has to break and reform in order after a rotation. But if I were to have something like this and do the same thing, those are chemically equivalent. Thermally, they're a little different, just because, but they're the same chemical. They're the same formula, same bond structures and everything. It's just everything's rotated around the sigma bond. Okay. The same kind of orbital hybridization that accounts for the methane structure also accounts for the bonding together of carbon atoms into chains and rings to make possibly many millions of organic compounds. Ethane, C2H6, is the simplest molecule containing a carbon-carbon bond. We can picture the ethane molecule by imagining the 2 carbon atoms bond to each other by head-on sigma overlap by an sp3 hybrid orbital from each. The remaining 3 sp3 hybrid orbitals on each carbon overlap with the 1s orbital of 3 hydrogens to form the 6 CH bonds. Sorry, one sec. The CH bonds in ethane are similar to those in methane, although a bit weaker, 421 kilojoules per mole for ethane versus 439 kilojoules per mole for methane. The CC bond is 153 picometers in length and has a strength of 377 kilojoules per mole. All the bond angles of ethane are near although not exactly at the tetrahedral value of 109.5. That's because things are moving. So there's two sp3 hybrid carbons. So as they get closer together, they start to hybridize like this. They start to attract each other like this. And then you get the bond. And then you get your angles between certain things. So, uh, problem 1.8. Draw a line bond structure for propane. Predict the value of each bond angle and indicate the overall shape of the molecule. Okay, so we're going to look at ethane for this. And I'm going to go ahead and draw this. Line bond. Boop, boop. So it looks like the angle between the hydrogens and the carbons are actually greater on the terminus, the terminal sides. Based on this, they go from 109.5 to 111.12. So I'm guessing that's going to be the same for all of both the end ones. 11 or greater. Oh, but however, it depends. It actually is going to depend because you're going to have two hydrogens. So one of them is going to be on a dash, one's going to be on a wedge. And it just really depends on how they orient. That's kind of a bad question. The overall shape, it's all going to be, everything's going to be a tetrahedral center. Convert the following molecular model of hexane, a component of gasoline, into a line bond structure. Boop, 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 boop. Done. Okay. 1.8. sp2 hybrid orbitals in the structure of ethylene. The bonds we've seen in methane and ethane are called single bonds because they result from the sharing of one electron pair between bonded atoms. It was recognized nearly 150 years ago, however, that carbon atoms also form double bonds by sharing two electron pairs between atoms, or triple bonds by sharing three electron pairs. Ethylene, for instance, has a structure H2C double bond CH2 and contains a carbon-carbon double bond, while acetylene has a structure HC triple bond CH and contains a carbon-carbon triple bond. How are multiple bonds described by valence bond theory? When we discussed sp3 hybrid orbitals in section 1.6, we said that the four valence shell atomic orbitals of carbon combine to form four equivalent sp3 hybrids. Imagine instead that the 2s orbital combines with only two of the three available 2p orbitals. Three sp2 hybrid orbitals result and one 2p orbital remains unchanged. Like sp3 hybrids, sp2 hybrid orbitals are unsymmetrical about the nucleus and are strongly oriented in a specific direction so they can form strong bonds. The three sp2 orbitals lie in a plane at angles of 120 degrees to one another, with the remaining p orbital perpendicular to the sp2 plane, as shown in figure 1.14. So the sp2 plane, basically all three of these sp2 orbitals, if you were to put like a little square or a triangle or any flat shape, it would actually cut through all of it nicely like that and split that top. This red part would be up top, and then this blue part would be at the bottom. So like as you can see right now, you're looking at just a top view. Yeah, so that's the whole plane. When two carbons with sp2 hybridization approach each other, they form a strong sigma bond by sp2 head-on overlap. At the same time, the unhybridized p orbitals interact by sideways overlap to form what is called a pi bond. The combination of an sp2 sigma bond and a 2p pi bond results in the sharing of four electrons and the formation of a carbon-carbon double bond. Note that the electrons in the sigma bond occupy the region centered between nuclei, while the electrons in the pi bonds occupy regions above and below a line drawn between nuclei. To complete the structure of ethylene, four hydrogen atoms form sigma bonds with the remaining four sp2 orbitals. Ethylene thus has a planar structure with HCH and HCC bond angles at approximately 120 degrees. The actual values are 117.4 for the HCH and the 121.3 for the HCC. Part of that is the size of things because they're not all the same size. Hydrogen's actually pretty small compared to carbon, but hydrogen's also more electronegative by a few decimal points uh, than carbon, and so that's going to shift things just a little bit. That's why they're not 120. Each CH bond has a length of 108.7 picometers and a strength of 464 kilojoules per mole. Yeah, and so what we're seeing here is before, so I'll go ahead and do plus equals. And basically what happens is just you get these two guys come in at each other and then they bond right there. And then you have your p orbitals are close enough to essentially delocalize the electrons between the two carbons. So instead of the electrons being held together by one of the atoms in like a normal Lewis structure, what's actually happening is the electrons are flowing back and forth between the two carbons, and it's being shared. And that's actually important for aromatic molecules in the future and conjugated um, alkene systems, like dialkenes, trialkenes, and so on. As you might expect, the carbon-carbon double bond in ethylene is both shorter and stronger than the single bond in ethane because it has 4 electrons bonding the nuclei together rather than 2. Ethylene has a CC bond length of 134 picometers and a strength of 728 kilojoules per mole, versus a CC length of 153 picometers and a strength of 377 kilojoules per mole for ethane. The carbon-carbon double bond is less than twice as strong as a single bond because the sideways overlap in the pi part of the double bond is not as great as the head-on overlap of the sigma part. All right, worked example 1.3, drawing electron dot and line bond structures. Commonly used in biology as a tissue preservative, formaldehyde CH2O contains a carbon-oxygen double bond. Draw electron dot in line bond structures for formaldehyde and indicate the hybridization of the carbon orbitals. Okay? So we're going to do electron dot. Do O H SP2. And that's just because I know it. Oh, I forgot the. I always just assume lone pairs, but it's always good to put them in. There it is. All right, problem 110. Draw a line bond structure for propene. Indicate the hybridization of the orbitals on each carbon and predict the values of each bond angle. So instead of line bonds, I'm just going to do. I'm calling it. What do we call it? Skeleton structure. That's what my organic chemistry professor called it. This is what I call. It has the other name. Starts with the M, I think, or K. But this is SP2, SP3, SP3, SP2. Those are both SP2 hybridized. Predict the value. SP2s are going to be roughly 120. SP3s are going to be roughly 109.5. But it's going to be different from that. Draw a line bond structure for 1,3-butadiene. Oh, there's a diene right there. So it's going to look like, I'm just going to do skeleton structure. I'm going to do it like this. Another way to draw it. It's just 2 ways. But that's just how you rotate it. But anywho, that's 1,3-butadiene. and indicate the hybridization of the orbitals on each carbon. So it's going to be sp2, 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 sp2. Oh, okay. That's probably why. I never thought of it that way. So this is a conjugated diene, um, meaning there are actual resonance structures for this. Basically, I can draw it. I'll show an example like that. Like that. Oh, no. No, I shouldn't say that. It's going to be more like this. Tiny little bit. It's going to go this way. But it's going to look like carbanion. Learn that soon. Problem 112. Molecular orbital of aspirin, acetyl salicylic acid, is shown. Identify the hybridization of the orbitals on each carbon atom in aspirin and tell which atoms have lone pairs of electrons. Hybridization of the orbitals on each carbon. Okay. These are all sp2. That's a benzene. And these two, sp3. That one, sp2. Tell which atoms have lone pairs. All the red ones have lone pairs. Okay. 1.9, sp hybrid orbitals in the structure of acetylene. In addition to forming single and double bonds by sharing 2 and 4 electrons, respectively, carbon can also form a triple bond by sharing 6 electrons to account for the triple bond in a molecule such as acetylene, HC triple bond H. We need a third kind of hybrid orbital, an sp hybrid. Imagine that instead of combining with 2 or 3 p orbitals, a carbon 2s orbital hybridizes with only one single p orbital. 2 sp hybrid orbitals result, and 2 p orbitals remain unchanged. The 2 sp orbitals are oriented 180 degrees apart on the right-left axis, while the p orbitals are perpendicular on the up-down axis and the in-out axis, as shown in Figure 116. Yep. So this will be like A star, B star, C star. So that's how they connect. That's how the lobes work. Although I did stars and not stars kind of backwards, but whatever. When 2 sp hybridization or hybridized carbon atoms approach each other, sp hybrid orbitals on each carbon overlap head-on to form a strong sp-sp sigma bond. At the same time, the pz orbitals from each carbon form pz-pz pi bond by sideways overlap, and the py orbitals overlap similarly to form a py-py pi bond. The net effect is the sharing of 6 electrons and formation of a carbon-carbon triple bond. Each of the 2 remaining sp hybrid orbitals forms a sigma bond with hydrogen to complete the acetylene molecule. And I know that looks crazy, but it's basically just, it's having you have this, and these guys are straight up and down. Now imagine you have the wedge and a dash, wedge and a dash. Oops. So this, I'll connect them with different colors. Red. This one connects with that one, and then that forms the bridge, which this is the same thing. That makes that bridge. And then you have another bridge, do it in green, from right here to right there. So the tips of those guys, and that's going to come out at away, like outside of the plane of the screen. And then you have this one, which will be more, it'll be like if you were to go deeper into the screen. And that's kind of what that's what's happening there. So you have the sideways overlap from 2 different perpendicular p orbitals. As suggested by sp hybridization, acetylene is a linear molecule with HCC bond angles of 180 degrees. The CH bonds have a length of 106 picometers and a strength of 558 kilojoules per mole. The CC bond length in acetylene is 120 picometers, and its strength is about 965 kilojoules per mole, making it the shortest and strongest of any carbon-carbon bond. A comparison of sp2, and sp3 hybridization is given. And it just shows bond lengths and stuff. 110, hybridization of nitrogen, oxygen, phosphorus, and sulfur. The valence bond concept of orbital hybridization described in the previous 4 sections is not limited to carbon. Covalent bonds formed by other elements can also be described using hybrid orbitals. Look, for instance, at the nitrogen atom in methylamine, an organic derivative of ammonia, and the substance responsible for the odor of rotting fish. The experimentally measured HNH bond angle in methylamine is 107.1 degrees, and the CNH bond angle is 110.3 degrees, both of which are close to the 109.5 degree tetrahedral angle found in methane. We therefore assume that nitrogen forms 4 sp3 hybrid orbitals just as carbon does. One of the 4 sp3 orbitals is occupied by 2 non-bonding electrons, and the other 3 hybrid orbitals have 1 electron each. Overlap of these 3 half-filled nitrogen orbitals with half-filled orbitals from other atoms gives methylamine. Note that the unshared lone pair of electrons in the 4th sp3 hybrid orbital of nitrogen occupies as much space as an NH bond does, and is very important to the chemistry of methylamine and other nitrogen-containing organic molecules. And so it's just showing that the nitrogen is actually in the same configuration as methane. However, instead of hydrogen being on top of it, you have a lone pair of electrons. And so if I were to draw, let's go back to black. If I were to draw this, there's a lone pair just kind of hanging out right up there. Okay, like the carbon atom in methane and nitrogen atom in methylamine, the oxygen atom in methanol, methyl alcohol, and many other organic molecules can be described as sp3 hybridized. The COH bond angle in methanol is 108.5, very close to the 109.5 tetrahedral angle. 2 of the 4 sp3 hybrid orbitals on oxygen are occupied by non-bonding electron lone pairs, and 2 are used to form bonds. And so this is a wedge. So on a dash, I'm going to have a lone pair, and then up here, I'm going to have a lone pair straight up into the plane. Okay. The thing is the lone pairs are not, you don't see them like you do another atom bonded, because the distance is so much further. Lone pairs are much closer to the nucleus than a bonded atom. In the periodic table, phosphorus and sulfur are the 3rd row analogs of nitrogen and oxygen, and the bonding in both can be described using hybrid orbitals. Because of their positions in the 3rd row, however, both phosphorus and sulfur can expand their outer shell octets and form more than the typical number of covalent bonds. Phosphorus, for instance, often forms 5 covalent bonds, and sulfur often forms 4. Phosphorus is most commonly encountered in biological molecules and compounds called organophosphates, which contain a phosphorus atom bonded to 4 oxygens, with one of the oxygens also bonded to carbon. Methyl phosphate, CH3OPO3 2- is the simplest example. The OPO bond angle in such compounds is typically in the range of 110 to 112, implying sp3 hybridization for phosphorus orbitals. Sulfur is most commonly encountered in biological molecules, either in compounds called thiols, which have a sulfur atom bonded to 1 atom, or 1 hydrogen and 1 carbon, CSH, or in sulfides, which have a sulfur atom bonded to 2 carbons, CSC, produced by some bacteria. Methane thiol is the simplest example of a thiol, and dimethyl sulfide, H3CSCH3, is the simplest example of a sulfide. Both can be described by approximate sp3 hybridization around sulfur, although both have significant deviation from the 109.5 degree tetrahedral angle. Yeah, 96.5, 99.1. It's pretty intense there. Problem 114. Identify all non-bonding lone pairs of electrons in the following molecules and tell what geometry you expect for each of the indicated atoms. Oxygen and dimethyl ether, that's sp3. And they're all on oxygen. And then B, the nitrogen atom in trimethylamine, H3CN, CH3, and CH3 down below. So that's going to be sp3 hybridized with a lone pair on the nitrogen. And then the phosphorus atom in phosphine, PH3. P, oop, oop, oop. Is there 2 or 3? Just 2? Yeah, I think this is sp3 hybridized. And then the sulfur atom in the amino acid methionine, that's also going to be sp3 hybridized. It's all sp3. I hate it when it's easy like that because it feels like a trick question. 111. Describing chemical bonds, molecular orbital theory. We said in section 1.5 that chemists use two models for describing covalent bonds, valence bond theory and molecular orbital theory. Having now seen the valence bond approach, which uses hybrid atomic orbitals to account for geometry and assumes the overlap of atomic orbitals to account for electron sharing, let's look briefly at the molecular orbital approach to bonding. We'll return to this topic in chapters 14 and 15 and 30 for a more in-depth discussion. Molecular orbital theory, or MO theory, describes covalent bond formation as arising from a mathematical combination of atomic orbitals, wave functions, on different atoms to form molecular orbitals, so called because they belong to the entire molecule rather than to an individual atom. Just as an atomic orbital, whether unhybridized or hybridized, describes a region of space around an atom where an electron is likely to be found, so a molecular orbital describes a region of space in a molecule where electrons are most likely to be found. Like an atomic orbital, a molecular orbital has a specific size, shape, and energy. In the H2 molecule, for example, two singly occupied 1s atomic orbitals combine to form two molecular orbitals. There are two ways for the orbital combination to occur, an additive way and a subtractive way. The additive combination leads to a formation of a molecular orbital that is lower in energy and roughly egg-shaped, while the subtractive combination leads to a molecular orbital that is higher in energy and has a node between the nuclei. Note that the additive combination is a single egg-shaped molecular orbital. It is not the same as the two overlapping 1s orbitals of the valence bond description. Similarly, the subtractive combination of a single molecular orbital with the shape of an elongated dumbbell. So you have two 1s orbitals, you add them together, and so you create two possibilities, the bonding and the non-bonding, but the electrons are going to fill lower energy first, and so since there's two valence electrons, they fill that first energy level first. If we had two more electrons, basically if you add energy to the system, that's how the bond breaks. If you added the however much energy it takes to break the bond, that's how much energy you need to fill those orbitals. So cool stuff. The additive combination is lower in energy than the two hydrogen 1s atomic orbitals and is called a bonding MO because electrons in this MO spend most of their time in the region between the two nuclei, thereby bonding the atoms together. The subtractive combination is higher in energy than the two hydrogen 1s orbitals and is called the anti-bonding MO because any electrons it contains can't occupy the central region between the nucleus where there is a node, and thus can't contribute to bonding. The two nuclei therefore repel each other, just as bonding and anti-bonding sigma molecular orbitals result in the head-on combination of two s atomic orbitals in H2. So bonding and anti-bonding pi molecular orbitals result from the sideways combination of two p atomic orbitals in ethylene. As shown in figure 119, the lower energy pi bonding MO has no node between nuclei and results from the combination of p orbital lobes from the same algebraic sign. The high energy pi antibonding MO has a node between nuclei and results from the combination of lobes with opposite algebraic signs. Only the bonding MO is occupied and the higher energy antibonding MO is vacant. We'll see in chapters 14, 15, and 30 that molecular orbital theory is particularly useful for describing pi bonds in compounds that have more than one double bond. So there it is right there. Yep, so basically if you put two of the atoms next to each other before they start to interact, they have their energy. But close enough, they'll combine, and they'll have those two possibilities, but the electrons are going to feel the lower energy first, and because what we see is this is what happens, not this, except without extra energy. If this is what happens, then we know the electrons are feeling the lower energy first, and this is lower energy than that. Because then all we have to do is just add some energy. These electrons will both excite and then turn into this, and then turn back into that. Okay, 112, drawing chemical structures. Let's cover just one more point before ending this introductory chapter. In the structures we've been drawing until now, a line between atoms has represented the two electrons in a covalent bond. Drawing every bond and every atom is tedious, however, so chemists have devised several shorthand ways for writing structures. In condensed structures, carbon-hydrogen and carbon-carbon single bonds aren't shown. Instead, they're understood. If a carbon has 3 hydrogens bonded to it, we write CH3. If a carbon has 2 hydrogens bonded to it, we write CH2, and so on. The compound called 2-methylbutane, for example, is written as follows. Okay, note that the horizontal bonds between carbons aren't shown in condensed structures. Oh, shoot, condensed. That's where you omit the line, but you keep drawing the symbols. Okay. Skeletal structures. Okay, there it is. Sorry. Condensed structures. CH3, CH2, and CH units are simply placed next to each other, but vertical carbon-carbon bonds, like that of the first of the condensed structures drawn above, is shown for clarity. Notice also that the second of the condensed structures, that the two CH3 units attached to the CH carbon are grouped together as CH3, 2. Ouch. Hold on. Even simpler than condensed structures are skeletal structures such as those shown in Table 1.3. The rules for drawing skeletal structures are straightforward. 1. Carbon atoms aren't usually shown. Instead, the carbon atom is assumed to be at each intersection of 2 lines and at the end of each line. Occasionally, a carbon atom might be indicated for emphasis or clarity. Rule 2. Hydrogen atoms bonded to carbon aren't shown. Because carbon always has a valence of 4, we mentally supply the correct number of hydrogen atoms for each carbon. Atoms other than carbon and hydrogen are shown. One further comment, although such groupings such as CH3, OH, and NH2 are usually written with the C, O, and N atom first and the H atom second, the order of writing is sometimes inverted to H3C, HO, and H2N if needed to make the bonding connections clearer. Larger units such as CH2CH3 are not inverted, though we don't write H3C CH2C because it would be confusing. There are, however, no well-defined rules that cover all cases. It's largely a matter of preference. Yep, it sure is. Worked example 1.4. Interpreting a line bond structure. Carvone, a substance responsible for the odor of spearmint, has the following structure. Tell how many hydrogens are bonded to each carbon and give the molecular formula of carvone. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. C9. So that's going to be, and then the number of hydrogens I'll do in yellow. 3, 2, 0, 1, 2, 0, 0, 3, 1, 2. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. And 1 oxygen. Did I do that right? Yep. Oh, no, I missed one. Which carbon did I miss? Ah, terminal carbon right here. 10. That's right. How many? I'm fine getting things wrong because I know how to find out how to be right. So, problem 115. How many hydrogens are bonded to each carbon in the following compounds, and what is the molecular formula of each substance? How many hydrogens are bonded to each carbon in the following compounds? 1, 0, 1, 1, 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9 are attached to carbon. And this is C6, 7, 8, 9, C9, C9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. NO3. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. C6, H21. C6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. O2. I might have missed a hydrogen somewhere, but that's all right. Propose a skeletal structure for compounds that satisfy the following molecular formulas. There are more than one possibility. Okay, C5H12. You have 1, 2, 3, 4, 5. 1, 2, 3, 4. 1 there. And then if I were to put it here instead, it's the same as this molecule, so that's 2. And then 2, 3. Boop, boop. Okay, C2H7N. That one, I think that's actually the only one I can do. So then, C360, you can have, or and then C4H9CO. There's 3 that I can think of. All right, chemistry matters. Let's read it. Organic foods, risk versus benefit. Oh, God, I totally did not say that right. Risk versus benefit. Contrary to what you may hear in supermarkets or on television, all foods are organic. That is, complex mixtures of organic molecules. Even so, when applied to food, the word organic has come to mean an absence of synthetic chemicals, typically pesticides, antibiotics, and preservatives. How concerned should we be about traces of pesticides in the food we eat, or toxins in the water we drink, or pollutants in the air we breathe? Life is not risk-free. We all take many risks each day without even thinking about it. We decide to ride a bike rather than drive, even though there is a 10 times greater likelihood per mile of dying in a bicycling accident than in a car. We decide to walk downstairs rather than take an elevator, even though 32,000 people die from falls each year in the United States. Some of us decide to smoke cigarettes, even though it increases our chances of getting cancer by 50%. But what about risks from chemicals like pesticides? One thing is certain: without pesticides, whether they target weeds, insects, or molds and fungi, crop production would drop significantly. Food prices would increase, and famines would occur in less developed parts of the world. Take the herbicide atrazine, for instance. In the United States alone, approximately 100 million pounds of atrazine are used each year to kill weeds in corn, sorghum, and sugarcane fields, greatly improving the yields of these crops. Nevertheless, the use of atrazine continues to be a concern because traces persist in the environment. Indeed, heavy atrazine exposure can pose health risks to humans and some animals. Because of these risks, the United States Environmental Protection Agency has decided not to ban its use because doing so would result in lower crop yields and increased food costs, and because there is no suitable alternative herbicide available. How can the potential hazards from a chemical like atrazine be determined? Risk evaluation of chemicals is carried out by exposing test animals, usually mice or rats, to the chemical and then monitoring the animals for signs of harm. To limit the expense and time needed, the amounts administered are typically hundreds or thousands of times greater than those a person might normally encounter. The results obtained in animal tests are then distilled into a single number called LD50, the amount of a substance per kilogram of body weight that is a lethal dose for 50% of the test animals. For atrazine, the LD50 value is between 1 and 4 grams per kilogram, depending on the animal species. Aspirin, for comparison, has an LD50 of 1.1 grams per kilogram, and ethanol is an LD50 of 10.6 grams per kilogram. There's some LD50s for some of the things. So should we still use atrazine? All decisions involve trade-off, and the answer is rarely obvious. Does the benefit of increased food production outweigh possible health risks of a pesticide? Do the beneficial effects of a new drug outweigh a potentially dangerous side effect in a small number of users? Different people will have different opinions, but an honest evaluation of facts is surely the best way to start. As of June 2022, atrazine was still approved for continued use in the United States because of the EPA believes that the benefits of increased food production outweigh the possible health risks. At the same time, atrazine is little used, though not banned in the European Union. All right, that's it. And that's everything. And I'll do these additional problems another time, maybe as part of the TikTok stuff. Actually, that'd be a good idea to do. Okay. Does this come with answers at all? That way I can at least double check what I did. Let's just double check real quick. I'm going to go to content. Answer key 1187. I could have just gone down here. Oh, cool. Yeah, so it does have all the answers. Nice. Okay, cool. So that's actually, I think what I'll do is I'll stop doing I'll do the example problems, but not the actual exercises from now on. And then just to get content on the TikTok, just to get used to using the platform, I will do all the problems, every single one of them. I'll make a TikTok for each freaking one. Cool. Okay. And then my TikTok, if I remember right, do I have the phone right here? Yeah, let me just double check it real quick. That way, if anybody watches it. TikTok. Randomization. So this is what my TikTok name is. Right now, I'm just doing workouts, just little body workouts that I can do while sitting in a chair. So I'm doing that to maybe inspire some of my family members to at least start building up some of that strength again. Get some energy back, because a lot of my family is pretty lazy. I don't want to say lazy, but they're we're all lazy. But I've been overcoming it. But my other family members are. Um, I just like to inspire them in case they want to have more energy and just have more ability each day. So, all right, that's it. Boom. 50 minutes. Nice. And then boop.